Hello and welcome to our second chapter in physics. This time we will be discussing the topic of kinematics. We're going to start out with a few definitions, so I'm going to go over those with you and give you a chance to write them down. First, kinematics is the study of motion without considering its cause. So in this chapter we're going to be looking at objects that are already moving, but we're not going to concern ourselves with what is making them move. We're only going to describe that motion. A frame of reference and a reference point you've probably had before, so we are going to be using a coordinate system to describe the motion of our object, and we will be defining that later. And then the reference point or the origin is your zero location in your coordinate system or your frame of reference. Be sure and pause the video if you need more time to write down these definitions. Since we are going to still talk about scalar and vector quantities in this chapter, I have a quick review for you. Remember that scalar quantities have only magnitude, which is just a number similar to a size, and vector quantities have both magnitude and direction. And I hope you remember that when we draw a picture of a vector, we're simply drawing an arrow that represents the direction. It has a tail and a head, and then any variable that's a vector quantity will have that variable listed. So in this case I did an A, and then we draw an arrow on top of that variable. The arrow that is drawn on top of the variable is always drawn pointing to the right, regardless of the actual direction of the vector. This is simply a way to let us know that we should be looking for a direction as part of our answer. Now we're going to get some new vocabulary. We're starting out with Roman numeral 2 on the word position. Go ahead and pause the video and write down the definition, and also number your number line just as I have done in the picture. So, when we talk about the position of an object, we are referring to that object's location in relation to the reference point. Position is going to be a vector quantity, and the reason for that is going to be determined by some of these questions that we have below. So for example, the first one asks you if you can distinguish the position from the guy and the girl. So our guy is standing over here, and the girl is standing over here. If you notice, both of them are 4 paces away from the origin. The way that you can distinguish them is by looking at a direction. So when we talk about a positive position, that's going to be anywhere over here in this direction, and that happens to be where the girl is standing. She is at positive 4. And then when we talk about the negative position, that's going to be anything to this side of our origin. So the guy is standing at negative 4. If you had simply said, oh, that person's standing at 4, that doesn't really tell us which side of the zero location we're talking about, because there are 2 4s there. And this is one of the things that makes position a vector quantity, because we need to know which side of the reference they are standing on. So positive will be to the right, and negative will be to the left for us. So when we write our numbers, a positive and a negative sign can represent a direction. And then obviously this last question, what is meant by a zero position? That just simply means at the origin. So remember, scalar quantities have only magnitude. Position is a vector quantity. It has a magnitude and a direction, and our positive or negative sign will indicate that direction. Our next set of vocabulary terms are going to be partnered together because they are similar to each other, but one is a scalar and one is a vector quantity. The first one is distance, and this refers to the total length that an object moves regardless of its direction. It is a scalar quantity, and the variable or symbol we're going to use is simply a lowercase d. Displacement, on the other hand, is a vector quantity, and it refers to an object's change in position. The symbol that we're going to be using will also be a D for displacement, but it's going to have an arrow on top of it. This will indicate that it's a vector, and when we look at an answer for a displacement, we should be looking for a direction as part of that answer. And then I made you some notes down at the bottom. Distance is measured continuously regardless of direction, and then displacement depends only on the final and initial positions. So now we're going to practice. Go ahead and take a moment to number your number line just as I've done in the picture, and we're going to do an example together. For our example, I'm going to say that a person is going to start out at the position of positive 2. So we're going to start here, and then they are going to walk over to the negative 4, and then we're going to walk to the positive 5 and stop. So let's identify our initial position. Hopefully you said that that was a positive 2. The final position was a positive 5. Now we want to find the total distance. So to do that, and get this erased here, we are going to count every step. So just follow along. We started here at positive 2. We took 1, 2, 3, 4, 5, 6 steps, and then because distance is a scalar and the direction does not matter, we're going to continue counting to the next place that the person walked. 7, 8, 9, 10, 11, 12, 13, 14, 15. So we would have a distance of 15. Now if we were looking at this to scale and measuring in the SI system, our metric unit for distance would be a meter. Okay. For displacement, on the other hand, we are only interested in the final and the initial position, so we're simply going to subtract. The final position was a positive 5, and then subtract. The initial position was a positive 2, and that's going to leave us, don't just say 3, it's a positive 3. And again, in the metric system, our displacement would have the same units as distance, which would be meters. So overall, this is telling us that from start to finish, my displacement was 1, 2, 3 steps in the positive direction. Let's do one more example together. Go ahead and number your number line, and this time we're going to have a person walk from -3 to +1 to -5 and back to -3. So let's count this out together. We started at -3 and we're just simply going to count 1, 2, 3, 4, change directions, 5, 6, 7, 8, 9, 10, change directions again, 11, 12. And notice that we ended up back where we started. So the total distance would be 12 meters. Okay, we counted every single step regardless of direction. Now let's look at the displacement. Remember that we're going to subtract the final minus initial position. The final position was -3, and we subtract, and the initial position is also -3. This leaves us with a displacement of 0. So any time that you see an object starting and ending in the same position, their displacement will be 0 regardless of how many meters they traveled for their distance. You should have a couple of more places in your notes, so go ahead and leave those blank for now, and we are going to do more examples in class together. So skip ahead to Roman numeral 3. For this Roman numeral, you'll notice that speed and velocity are paired together because one of them is a scalar quantity and one is a vector quantity, but they are similar to each other. So let's start with speed. Speed is the scalar quantity, and it's the ratio of the distance covered to the time it took. Notice that the word distance is included in the definition, and distance was a scalar quantity, so speed is a scalar as well. And you can remember it because speed and scalar both start with S. When we write our formula, we're going to have the lowercase letter v as the symbol for speed, and then distance over time. So you'll see in physics that a lot of times the definition for a word is simply the equation written out for you. So we've got ratio that tells us there's going to be a fraction, and it's of distance to time, so distance traveled to time taken. One thing we're going to do throughout the year is write our units in brackets for different quantities. So in this case, distance should be measured in meters and time is in seconds, so that makes the units for speed meters over seconds. Eventually we're going to work with graphs as well, and when we get to position time graphs, you'll see that the speed is going to be the absolute value of the slope. So I hope you remember how to find the slope of a straight line because we're going to be seeing that later. Next, we have velocity, and you'll notice that it's really similar to speed, but we're replacing the word distance with displacement. And notice on the formula, we now include the vector notation for our vector quantities that are in that particular formula. So again, we're looking at a ratio, so we know there's going to be a fraction, and it's of displacement to time. So both velocity and displacement are the vector quantities. Time is a scalar. And you'll also see that it should be easy to remember that velocity is a vector because they both start with the letter V. And again, when we do work our way up to graphs, a position time graph, if we look at the velocity for this one, and I just saw this in your notes, go ahead and scratch this word out right here. This should be the velocity is, and then it's not the absolute value of the slope. The velocity is the actual slope, whether it's positive or negative, of a position time graph. So I'm not sure if it looks that way on your copy of the notes, but just make sure that you get that correction if you need to make it. So I'm going to do an example problem with you. We are looking at the length of a tennis court, and in this case, we've got a distance, which is our length, of 2,400 centimeters. And remember that distance should be measured in meters, so we do want to convert that to meters. And to do so, we can simply use our conversion factor, and that'll give us 24 meters. You'll notice that the conversions and the powers of 10 and prefixes will carry over throughout the year, so make sure that you still review those from Chapter 1. We're also given a time of 52 seconds, and we are asked to find the object's speed. Okay. So what I did was wrote down all of the variables and numbers that were given, and then I wrote down our unknown, and now we're going to look at our equation. So the formula for speed is simply distance over time, and we're going to have a distance of 24 meters and divide by a time of 0.52 seconds. This leaves us with a speed of 46 meters per second. Go ahead and pause the video and try example problem number 2. Notice that you're given units of kilometers and hours, but you're asked to find the speed in meters per second, so don't forget to make those conversions. If you have problems with this one, make sure that you ask me about it in class and we can go over it together. I think you should be able to do number 3 on your own as well. This time you are solving for how far, so you're going to be looking for a distance. You will need to rearrange that formula and solve for distance, but go ahead and try the problem on your own. Make sure that you make a note of your answer and ask me about it in class to make sure that you are correct. Let's do number 4 together. For this problem, you see that a bicyclist rides 30 kilometers north and then turns around and rides for 10 kilometers south. You're given the time it takes for the trip, and you are asked to find the velocity. Remember, velocity is displacement over time, and we are going to need to find the displacement first. So let's go ahead and do that. I hope you remember that displacement is subtracting the final minus initial position. Since our distances that are traveled are in opposite directions, that's going to make them displacements, and we need to assign a direction for each of those. So I'm going to say that north is going to be positive and south is going to be negative. So if we were to look at the vector diagram for that, I would have 30 kilometers north, which would be a positive 30, and 10 kilometers south, which would be a negative 10. You could find the displacement by looking at your vector diagram if you were to draw a picture, or we can also plug in those numbers. Either way, you should get an answer of 20 kilometers north or a positive 20 kilometers. Now that we have a displacement, we can plug this into our velocity formula. Once you plug those numbers in, you should get an answer of 16. But remember, it's a vector quantity, so we want to include that direction of positive 16 kilometers per hour. Now remember, speed and velocity should both be measured in meters per second, so we do want to make that conversion. You should know how to convert from kilometers per hour to meters per second from Chapter 1, so go ahead and take a moment and make that conversion, please. You should have got an answer of positive 4.4 meters per second. So overall, their velocity was 4.4 meters per second in the positive direction, which we had labeled as north earlier. You do have a space in your notes for some number line examples. I'm going to do one of those with you in this video, and then we will cover more examples in class together.